Hello everyone. In the previous video, we have discussed about what is the partition, what is bounded functions, what is the norm of partitions, how to find length of each subinterval. Now, along with that, now in this video, in this demo, we are going to discuss the partition, refinement of the partitions. So, the word itself implies the definition of this. Suppose the P1 is the partition of closed interval AB. Always we are assuming the format of the interval as closed interval AB where A is less than B. And there is another partition of this closed interval AB as P2, capital P1, capital P2. And since there are infinite number of points in any closed interval, so we have so many partitions for any interval. So family of that partition will be always denoted by P of AB. This is the set of all partitions of closed interval AB. So both belong to this family, the family of all partitions. Then if P1 is a subset of P2, then P2 is called as refinement over P1. This P2 is the refinement of P1. P2 is refinement of P1. For example, suppose I will take the interval in the real line as 0 and 1, 0 and 1, and I have partitioned this point as x0, another point x1, x2, x3, and suppose this is x4. So this partition I call it as P1. x0, x1, x2, x3 and x4. If I add some more points here, suppose I will add some y dash, then the another partitions will be like this: x0, x1, x2, y dash, x3 and x4. Look at this, these all are the element of P2 except this y dash, all are element of P2. That means you are making refinement of this, and you can continuously refine all these, the partition you can add more points. So P2 is called refinement of partition P1. This is the definition. There is another term regarding the what is a common refinement. Let P1 and P2 be two partitions of any closed interval AB. Then one can see that the P1 union P2 is also partition of closed interval AB. This P1, besides first and last point will be common, or there may be other common points also, but whatever union, that also constitutes the partition for closed interval AB. Then naturally P1 is a subset of P1 union P2 and P2 is subset of P1 union P2. So P1 P2 has the common refinement. This both have common refinement. So P1 union P2 is known as common refinement. This is known as common refinement of both P1 and P2. This P1 and P2 is known as common refinement of both P1 and P2. So this is all about the refinement of the partitions and common refinement. Okay, we'll have important remark here regarding these refinements. Important remarks: if P2 is refinement of, may be equal to these two sets, may be equal to, if P2 is refinement of P1, that is P1 is subset of P2, then we have to discuss about their norms. What is the norm of partition P1, and what about norm of partition P2? So this will be always less than or equal to P2, and I can verify this. Okay, I will have the closed interval AB, and suppose this is the partition, one partition, and I take I will assume that this has the largest distance. This distance I will call it as norm of first partition. If in the refinement, if the point is added somewhere here, till then it will be the highest value. So in that case the norm will be equal to. But if your refinement point is coming to here, then the length this and the other lengths as compared to this length, everybody is the of lesser lengths. So in the refinement, norm of P1 is always less than or equal to norm of P2 in the refinement. Okay, wait, I have to make corrections in that. Earlier has the greater norm, so P2 is less than or equal to P2 and logic is same. So earlier version has the largest length, but in the largest length if you add some points there, then the length may be reduced. That's why the norm of P2 is less than or equal to norm of P1. This is one remark. And second remark, in the partitions if you add sum of all I from 1 to n, this is coming b minus a. In the previous video we have discussed about this. So this is the remark about this refinement. Now I am going to define the upper and lower Darboux sums. The upper and lower Darboux sum. So what is it? So initially whatever functions you have, it should be the real valued on closed interval AB and should be the bounded functions. Once it is bounded function, then we can find the maximum, that is supremum of that function in that particular interval, and infimum, that is minimum value of the function in that interval. Because f is bounded, we can have highest and least value in that interval. Then we have partition x0 equal to a, x1, x2, let us have n plus 1 points. So this is a. Then we have partitions. These points are called partition points, and the subinterval I will denote it as IR. So how it is? XR minus 1 XR. The first interval will be x0 x1, like that. The length of each interval will be denoted by delta R, that is XR minus 1. Now since this function is bounded on closed interval, it has to be bounded on these small parts of that closed interval. Otherwise, if it is not bounded on this, how could it bounded in on closed interval AB? So your function is bounded on each R, on each subinterval. That means on each subinterval function has maximum value and minimum value. So I will denote small mr for the infimum of f on the interval IR, and I will denote mr, that is the supremum of the function f on that interval IR. And likewise I denote the small m as infimum of function f on closed interval AB, and capital M the supremum of function f on closed interval AB. At present we are not going to apply in the definition, just keep in mind. So as your function is bounded on this closed interval AB, it has to be bounded on each subinterval. Otherwise what will happen? Suppose the function is not bounded on subinterval, then how could one say that it is bounded on the larger interval? So compulsorily it has to be bounded. Since it is bounded in each and every subinterval, there is infimum and supremum for that function by the boundedness of that function. So use this fact to define upper Darboux sum, and the length of each interval is known to us. So I am defining the upper Darboux sum as well as lower Darboux sums. Let me define first the lower Darboux sum. The sum. So okay, on the first interval length is delta 1 and the infimum value of function is m1. On the second interval the infimum value is m2, I have denoted here, and length is delta 2. and so on. There are total n intervals, so you'll get n infimum and n supremum values. So this sum is called as upper Darboux sum. It is denoted by UPF like this, corresponding to that partition P. This P is capital and your function. The upper Darboux sum of the function f with respect to partition P is calculated like this. So in short, how I can define it? The upper Darboux sum is denoted by UPF and it is defined by small mi delta I from 1 to n, where this mi is the infimum of the function f on the subinterval IR and delta I is the length of subinterval IR. So this sum is this sum is okay. This is not upper Darboux sum. It should be the lower Darboux sum because the lower values I have taken. So sorry for that. So I'll take LPF here. Secondly, I need to define the upper Darboux sum. So it is denoted by UPF. This will be the upper Darboux sum. It is denoted by UPF, and m1 is the highest value or supremum of on first interval multiplied by length of that interval, m2 multiplied by delta 2, and so on, mn delta n. So it will be summation mi delta I from 1 to n. So these are both definitions for upper Darboux sum and lower Darboux sums, and this plays important role in the defining the upper Riemann integral and lower Riemann integral. So in the next lectures we are going to discuss important properties or stating relation between these two lower and upper Darboux sums. So we'll continue in the next talk regarding properties of this. Till then we stop here. Thank you so much for listening.